Good afternoon. I'm Jack.
I'm Chris.
Today we're going to talk about improving screw compressor rotors, but more specifically, we'll be sharing with you a collaboration on this issue between rotor design and rotor manufacturing. Why are you here today? I imagine it's because you're interested in the exchange of knowledge. So consider this, the first law of knowledge. It identifies three states and what each should mean to us. There are things you know. When starting something new, this is your foundation. There are things you don't know. These are things you know you need. So plan and make the effort to learn them. And then the things you don't know. A colleague of mine observed that this is where the dragons live. So that brings us to the first law of dragon slaying. Everyone you meet knows something you don't, something you need to know. Learn from them. This could also be considered the first law of collaboration.
Our story is about an international collaboration on screw compressor development, which started with an open mind on both sides and a sharing of knowledge and questions which led to a rethink for both parties. Contrary to the usual rules of technical papers, much of the following is reported in a personal way, as our intention is to tell a story which we hope will be helpful to others considering embarking on collaboration, whether as designers, manufacturers, or academics. Engineering of complex precision products works best when key people are involved from the beginning. This minimizes the risk of expensive mistakes. The design is then based on a full understanding of all the factors which affect the end product.
For me, our story started in the late 1970s with Trane's vision to offer water chillers fitted with screw compressors. At that time, we had no experience with screw compressors, so we became a licensee of SRM, who designed our first compressor, providing grounding in many important principles.
John Holroyd founded his company around 1861. Not much is known about him, but we do know he had personal connections with Joseph Whitworth, and that his company made a wide variety of precision machine tools. Then, as a result of an interesting collaboration with SRM in Sweden in the 1950s, they developed the first rotor milling machine for Howden in Glasgow. They soon went on to supply machines and rotors to other companies who started making screw compressors under license from SRM. Rotor accuracy was crucial to compressor efficiency and reliability, and this had two requirements: accurate manufacture and accurate measurement. Holroyd's machines were built to a high standard of precision in all linear and rotary axes to achieve accurate helical movement of the rotor past the cutter. Cutter profiles were accurately ground using another dedicated Holroyd precision machine in combination with specially developed software for creating profiles to any design. Rotor tolerances were gradually getting tighter, but a persistent problem in the industry at that time was the lack of an accurate and repeatable method of rotor measurement. Clearance measurements were made using feeler gauges by highly skilled inspectors. The information was interpreted to indicate any adjustments needed to the tool shape and machine settings, but the method was only reliable to around 15 microns. This problem had to be addressed. Holroyd's MD was Ronnie Kershaw, a Rochdale man who had come up through the ranks in the company. He had a feel for getting people to work together. Ronnie had engaged the consultancy services of Professor Bob Milnrow of Huddersfield University, who had an excellent engineering background. Bob proposed a PhD research project with the aim stated simply as to find a better way of inspecting screw rotors.
Much of my time was spent on the assignment I had to develop a thermodynamic simulation for this new to us screw compressor. I thought it would be easy. I was wrong. I knew what I knew, and that was thermodynamic simulation. I had already developed a model for scroll compressors. But I quickly learned that I did not know the intricacies of rotor profile geometry. The roadblock was a mathematical analysis of profiles and the resulting characteristics of rotor pairs, things I would need for the simulation. I was struggling. Then, doing literature surveys in 1982, I found the book Schraubenpredictor by Professor Laurenz Rinder. I got a copy through our library, and as soon as I opened it, I could see it had just what I needed. It changed everything. I met Laurenz at the Technical University of Vienna and asked if he would teach us to design rotor profiles. I was impressed when he said, "I can teach you how I do it." In his book, he described a process where some elements of the profiles are specified from which, according to laws of gearing, remaining elements could be generated. But his approach in practice was to start with the basic rack, a shape conjugate to both rotors. I asked him why. He told me something I did not know that I didn't know. A good design will always consider the manufacturing process, and the rack is a surrogate for the profile cutting tool. Laurenz spent 2 months in La Crosse teaching and guiding us in execution of the first Trane design rotors. When we were done, Trane ordered prototypes from Holroyd.
After a decade teaching maths, physics and technology in schools, I was looking for a new challenge and applied for the PhD project under Bob Milnrow, and much to my surprise was accepted. This led to my first involvement with the company. Bob had an industrial background before and after his time at Cambridge and believed in the need for academics to address real industrial problems. He introduced us to the idea of transmission error, which is a source of noise in gears and, as we soon learned, in rotors. I knew nothing about screw compressor rotors. After spending some time on the shop floor and considering measurement options, the idea of using light was suggested. It seemed worth exploring, but I had to find if the viewing angle for all points around the profile was constant or varying. If the latter, the method would be impracticable. Mathematical modelling was required, and with the help of the university's computer centre under Bill McTaggart and many late nights, I eventually came up with a transverse model that showed the viewing angle to be constant for every point around the seal line. The key to this was the discovery that it was possible to construct a curved line which could be passed through the gap between the rotors in the direction of the tangent to the helix at the pitch line contact point. After months of head scratching, this was the light bulb moment. I then learned from Bob that my curved line was known in gear circles as the basic rack, which Jack and Laurenz Rinder had found key to their own developments. Consider conjugate profiles in the transverse plane as shown. In general, the profile of one rotor may be chosen arbitrarily and the conjugate profile for the mating rotor developed. But for any pair of conjugate profiles, there also exists a basic rack form, which is the conjugate form of a rotor of infinite radius. It can be derived from either rotor, and its pitch circle is a straight line. As the profiles rotate, the rack is translated in a direction perpendicular to the line of centers. But if the rotors are kept stationary and a succession of transverse profiles along the z-axis are viewed instead, as shown in the diagram, the results are identical. So the rack generates a curved shape consisting of lines parallel to the pitch line helix, all of which are tangent to the rotor surfaces at the seal line. In other words, for every point on the seal line between a pair of conjugate helical surfaces, there exists a common tangent which is parallel to the helix tangent at the pitch line. For each and every axial section through the rotor lobes, these tangents are the lines of sight, as shown. In the left diagram, the female lobe curves back rather threateningly towards the line of sight, but does not touch it. But then, my light bulb moment turned into bigger light problems. The three-dimensional seal line and the curved surfaces around it were a source of major optical distortions due to the effect of near-parallel reflective surfaces on the passage of the light. Fortunately, after nearly 2 years at the university's optical bench, these were overcome, and the work eventually led to a novel measuring machine, a world patent, and several published papers.
Chris and I worked together in a collaboration that was characterized by an informal agreement between our respective companies, this to support an ongoing dialogue between us and the efforts that might arise in the process. The foundations for this approach stem from viewpoints held by the two companies' management. Trane's engineering leader, Dave Eber, supported the principle of Trane being accountable for its products and was committed to a future where our engineering team would be responsible for all aspects of the compressor design.
Holroyd's managing director, Ronnie Kershaw, encouraged his engineers to get a fundamental understanding of customers' problems and needs. He said, "One has to make friends before making business."
I made my first visit to Holroyd's offices and factory in Milnrow in 1989. There I met many of the people I would work with, including Chris and tool designer Jack Hughes. Both would play roles in this story of our soon-to-be-born collaboration. And of course, I met our first Trane rotors for the first time. Our focus was clearance data for the rotor pairs in our order. We spent a good deal of time on the shop floor watching technicians as they demonstrated the process. They would spend a bit of time finding the right view, locate a point we had specified, measure the gap with feeler gauges, and record it on an inspection form. We talked about clearance results, but more importantly began to dig into why they were as they were. They're important for compressor performance and reliability, these factors being at odds with each other over what the gap size should be. As we talked, Chris and I noted that although Holroyd manufactured rotors, we were judging them by the gap that only exists when they're paired. We would need to understand the design and manufacture of individual rotors if we were to achieve proper clearances in rotor pairs. And at one point, Jack Hughes offered this opinion: "This design is easy to make. We would need to understand this in order to have it as a design intent." My engineering manager, Pete Leonard, was with me on my second visit in 1990. He met Chris and Holroyd's managing director, Ronnie Kershaw. Here are some excerpts from Pete's trip report on that visit. Chris is very competent and works well with everyone. He added Holroyd values Jack's input to Chris's clearance measurement project, and we, Trane and Holroyd, intend to support them by means of a dialogue between Chris and Jack. And finally, he noted, Ronnie arranged for us to spend a full day away from the plant with Chris so as to get to know him better on a personal basis in order to facilitate communication. This last statement embodied Ronnie's principle that one had to make friends before making business. The collaboration was as formally recognized as it ever would be. There wasn't a plan, no stated outcomes, no budget. Its primary aim was for Trane and Holroyd to have the right people together when and where it would be most beneficial to the separate but intertwined company goals.
Trane's inquiry for prototype rotors from Holroyd was the beginning of a most interesting and fruitful collaboration. Ronnie Kershaw saw an opportunity to invite Trane's expert Jack Sauls to see our methods and discuss ways forward which would benefit Trane's business and ours. Being still a new boy, I felt honoured to be asked to engage with a customer from such a major company in our field. Then, finding that this particular visitor was intensely interested in all he was seeing in the company, its people, and our little part of England, any nervousness I'd felt turned into enjoyment of our progress together. At our first meeting, Jack was invited to see my novel inspection method and showed a close interest. He told me about Professor Rinder and his use of the rack in his rotor design. It was clear our recent investigations had a lot in common. Trane's backlash issue was the stimulus for Holroyd to ask Bob to contribute, leading to the study of transmission error and the effects of relief and crowning, primarily related to noise but eventually also to address potential reliability issues. As far as we are aware, the first transmission error test ever carried out on rotors was during Jack's visit in March 1992, using test centres fitted with rotary encoders. The picture shows Jack rotating the rotors manually as Bob Milnrow captures the data. Jack's interest in this was a spur to include transmission error measurement in our optical rotor inspection machine.
I had never heard of transmission error, but here Bob and Chris were developing automated processes to measure it. Now I had a chance to see it in action. Also, it was quite an honor to have been given the job of rotating the rotors. The only requirement was to keep them turning, and I could do that. Bob and Chris had been thinking deep thoughts about transmission error, though. It could be a factor in compressor noise, they said. Now, that got my attention. Noise was an issue for our customers, and compressors could be a significant contributor. The collaboration had led us to an unexpected phase of discovery together.
Transmission error occurs in the driven component of a rotating pair of gears or rotors when its instantaneous angular position differs from the theoretical angular position determined by the gear ratio. It was possible to plot the forward transmission error, shown in blue, reverse transmission error in green, and backlash in black over a full engagement cycle. The errors shown are from geometrical errors in the rotors. This data was then processed using Fourier analysis to predict the rotor-generated noise to be expected in the compressor.
There were two interesting things we learned in the test program Chris mentioned. Holroyd made and measured several crowned male rotors paired with a single uncrowned female. That data showed crowning's effect on the magnitude of the transmission error and that there was an optimum crowning. Trane subsequently measured sound levels of a compressor with several of the rotor pair installed. This data showed that crowned rotors could provide a noise reduction on the order of 3 decibels. Holroyd and Trane had learned and put into practice much from the work carried out by Bob and Chris.
The benefits were confirmed in a similar collaboration some years later with another major US compressor company who measured noise reduction of 6 decibels. They bought the fully developed machine. But in addition to manufacturing deviations in the rotors, there are other sources of transmission error in a working compressor, as identified in items 7 to 10 here. In a collaboration with Miyakawa, Japan, all the deflections and misalignments were carefully estimated in advance. The rotor leads were then modified accordingly to minimize the predicted noise. The results were published in a joint paper by myself and Koichi Matsuo at this conference in 2013. The eventual machine was fully automated and named ARAC, Automatic Rotor Analysis Center. After a full statistical study, its measurement capability was shown to be well within the needs of manufacturing and was at least 10 times more accurate than feeler gauges. It was the subject of several conference publications, including Purdue Compressors in 2004. To quote Jack, "Whether made as pairs or individuals, the quality, i.e. suitability for purpose, of screw rotors results primarily from the geometry of the gap between them. The gap determines efficiency, reliability, and noise." Almost every profile design received from customers had one or more problem areas which had to be addressed. Otherwise, the profiles were either impossible to manufacture or would not give the clearances specified, and the rotors would be rejected. Sometimes rotor shapes had tight corner radii which could not be achieved or which caused excessive tool wear and frequent costly resharpening and replacement of the milling blades. Holroyd engaged the mathematical wizard from the Machine Tool Industry Research Association, MTIRA, to write the necessary software, CoPro, to calculate tool profiles and to correct rotor profile errors so that the workable tooling could be made, giving rotors which would have the required clearances. Customers were not usually involved in or even aware of this process. Fortunately, Trane's profiles did not have such problems.
Our collaboration spanned 10 years. It had several threads and many aha light bulb moments. Many of those happened simply because I had the opportunity to be at the offices and rotor shop in Milnrow. Every visit had a main reason, but significant benefit came from unplanned gatherings of interested parties from our two companies. The framework for most gatherings was the process for designing, ordering, and making profile cutting tools, and then the rotors themselves. So I'd like to share a few instances of these unexpected but beneficial consequences of being together. In the beginning, work flowed this way. Trane's profile design was communicated to Holroyd in a table of coordinates. Holroyd converted these to a format they required. This dictated by the program called CoPro at the time that would calculate the cutter profile. We had sent data several times, but it was only because of a more or less casual comment made by Mike Smith during a visit that I learned of this conversion. It was never mentioned to us because Holroyd felt that if that's the way the customer wanted to provide the information, then they would accommodate it. When I mentioned I felt that Holroyd should specify precisely what they would need to us so that we could provide the data in that format, Mike's response was, "No one ever asked us what we needed before." But that's what we did, and we began providing converted data directly to Holroyd without requiring them to do the conversion. We'd also learned that it was possible to design a rotor profile for which a rational tool form did not exist. When Holroyd found this to be the case, they would inform us and we would work together to redefine the profile details. It occurred to me that if Trane had a copy of CoPro as part of its design system, we could find and fix at least some of the issues before sending the data. We were never going to be tool designers, but we agreed that this would be beneficial for both companies. It wasn't necessarily easy. CoPro wasn't a product at the time, but we made the arrangements, got the training, and eventually embedded it into the process. So we ended up with something that looked like this. We would design the profile, we would convert the data and run CoPro to do the basic checks on tool quality. When we were satisfied, we would send the data. Holroyd would design the tool and make the tool, and then we could get on with the job of making the rotors. Making a rotor requires first making a wheel with the tool profile. This is mounted in a multi-axis machine where the rotor is milled or ground from a solid workpiece. The machine's axes are adjustable to locate, orient, and move the wheel relative to the workpiece, producing a three-dimensional multi-lobe helical screw rotor. It's probably obvious, but if the cutting tool and the machine settings are precisely in accordance with the design, the profile on the rotor will be as specified. That's true, of course, but in practice, this result is rare. Holroyd made many rotors for Trane, such as those with our transmission error study. In the real world, experimentation is time-consuming and expensive, so much so that studies are necessarily limited in terms of alternatives and number of samples. But there was this. CoPro, which calculates a cutting tool form and attendant machine axis settings from a rotor lobe profile, could be run in reverse. Given the cutting tool shape and the machine settings, a computational process can be executed to provide the rotor profile.
Even with a perfect tool profile shape and a perfect rotor blank mounted in the machine, there were errors which appeared during manufacturing caused by misalignment, run-out, or deflection of the rotor during cutting. CoPro was later adapted by Holroyd's Alan Stephen for modeling the entire machining process. The software was made available for sale to machine tool customers only under the name HPMS, Holroyd Profile Manufacturing Software. But some years later, Jack and colleagues came to question us about what appeared to be systematic rotor profile errors. The outcome was significant for both companies, as the investigation led to the surprising conclusion that a perfect milling tool shape did not guarantee a perfect rotor profile, and constant bulges on the round side of the male profile were baffling all concerned, and had certainly been unknown unknowns. Alan Stephen decided to make geometrical calculations of the lengths of the tool's contact path with the rotor and found that the lengths were quite different around the profile, which almost certainly explained why more metal was removed in those areas with longer contact paths. As these effects could not be avoided but were constant, a systematic compensation method was developed using geometric software specially written. This used an imperfect tool profile to produce a perfect rotor profile. This was a breakthrough for both companies and yet more evidence of the mutual benefits of a positive and collaborative investigation. Touch trigger probes allowed corrections to be made without unloading the rotor. Later, when scanning probes were added to the machines, rotors could be measured and errors compensated for, and in the case of dressable grinding wheels, these corrections could be applied to the profile shapes without unloading the rotor. A relevant paper was published in the ASME Nevada conference proceedings in 2007.
To address the limitations inherent in hardware testing, Trane developed a virtual manufacturing process. Here we have control over the tool form and machine settings and can carry out all manner of investigations. It was very instructive to run tests of the effective deviation of each axis on the rotor profile individually. An offset and a setting produced very distinct signature profiles. This simple example is from a study I reported at the 2000 Purdue Compressor Conference, where we can see here the effect of a shift in just one axis setting, the angle B. The tool allowed us to look at other, more complex and important questions. For example, what variations will the rotors face during production, and how will different designs react?
Holroyd provided guidance on what we might expect these variations to be, their magnitude, and what form of statistical variation they may take. With that, we proceeded to simulate production runs of 1,000 rotors. There was a virtual coordinate measuring machine within this factory to examine each sample and record information about its deviation from the design, identifying rejects, cases where profiles fell outside of our tolerances. These exercises were very informative. I must add here a nod to Professor Nicholas Stoshis. In order to get the function we needed, we had to embed the calculations of the tool form to the rotor form in our programs. This was something we couldn't do with CoPro, but Nicola had a startlingly short piece of code that we acquired that handled the task perfectly. The original Trane rotors had been in production for some time when a new project gave us a chance to consider another profile and the opportunity to use the virtual factory to assess manufacturing issues. In the study, we ran 1,000 samples each of the male and female rotors. Machine tool variation characteristics were guided by Holroyd. The criteria for comparing the options was the number of out-of-tolerance parts. For the original design, 77 female and 89 male rotors were unusable based on exceeding profile tolerances. With the new design, there were 100 female and 110 male rotors failing to meet the criteria. Overall, this was a 26% higher rate than with the original design. When Jack Hughes commented about the easy-to-make nature of our original profile, he explained it was because the rotor shop experienced less scrap and fewer reworks caused by out-of-tolerance parts than was the general experience. Years later, we were able to consider manufacturing in the design and could quantify Jack's observation of easy to make. I wish I could have the chance to show him these results.
We hope that by reflecting on our own collaborations and sharing insights, we may have been able to inspire and inform future collaborations between companies and universities for the benefits of both.
For engineering experts, we encourage you to seek and advocate for meaningful collaborations, even those that might be outside the lines in current organizational process guidelines. And to managers, encourage and support these ventures.
We hope we've convinced you that in the pursuit of engineering knowledge, one can't easily do it alone. A willingness to collaborate rather than compete can lead to identifying the unknowns and then to light bulb moments of discovery, resulting in both design improvements and manufacturing improvements with strong mutual benefits.
We've shared a collaboration between ourselves and our companies, but we both also have experience with supporting, attending, and contributing to engineering conferences. It's rare that attending one conference will bring the answer to the current big issue. Rather, regular attendance and interaction with peers is a form of ongoing collaboration, and we encourage students, engineers, and leaders to advocate for and support this.
So then, when future problems arise, the individuals know they have a route to finding solutions. Now, collaboration tools have changed over the years. Instead of fax machines, one can use Google Docs to create a joint presentation whilst thousands of miles apart, as we have done here, but the principles remain the same.
I was asked in the early 1970s what I thought were the biggest technology advances supporting our compressor design. I replied, the fax machine and the Boeing 747. Rapid communication over great distances and face-to-face time are both important elements of an effective collaboration. Travel gets much attention in budgets because of its expense. Its value might be difficult to quantify, but it's worth energetically advocating for and supporting.
As to whether we can claim to have succeeded in proving our point, we think the evidence from this case study is unequivocally yes.